Let's record, minimize, get rid of that. Where do we want to start? With 1?
Yeah.
Okay.
Actually, I think 1 through 4 we kind of went over last time, so we could start with 5.
These look familiar.
Yeah, we can start with 5 then.
Yeah, I don't know that we did. You understand the multiplicity concept? In other words, what's the answer to number 2? I don't know that we really did go over this.
It'd be like x plus 4, x minus 3. Oh, wait, no, it'd be x plus 4 3 times, so x plus 4 cubed.
Okay, good.
Yeah.
And that would give you the answer, yeah. And on number 3, what would the 2 factors be?
X plus root 10, x minus root 10, and then x plus root 6, x minus root 6.
Okay.
Yeah, we pretty much we went over those last time, so I think if we just start with number 5.
Where do you want to start? Which one?
Number 5.
Number 5? Okay. So find all of the roots. So there's 1. There's another. That one. Whenever it's all pluses, well, I shouldn't say whenever, but that's going to be imaginary solutions.
Okay.
And typically, incidentally, when you break down a high degree polynomial into its factors, when you get everything down to a linear factor like the first 2, but then you have what is called an irreducible quadratic. And typically you don't go to the trouble of breaking that down. In other words, that actually would be a more typical answer. But they do want us to break down that. So let's use the quadratic formula, plug it in. What do we get?
So you would get -4 plus or minus the square root of 4 squared minus 4, 1 and 16 over 2.
Okay, let's simplify that.
So,
minus
huh?
I think it's minus 48 inside. The discriminant is minus 48. 16 minus 64, all over 2. Now simplify minus 48.
7i.
Not 7. It's not 49.
Oh, right. So it'd be
what's the greatest factor of 48? In other words, here, let's talk about this for just a second. How we handle this. First step, always do this. Separate it into -1 times the positive square root. Because you know what that is. That's I. So now all you have to do is deal with that. Well, if you think about your perfect square numbers, any of those factors of 48?
16.
16 is the greatest one. 4 is also a factor. And we'd eventually whittle it down if we used 4, but we'll get there quicker if we use 16. So what we have here is I times the square, or 4 times square root of 3. And the way we typically write that is the I comes after. In other words, I would write that 4 root 3I. That is negative 48. Okay? So if I replace that with that, then I have 4 root 3I over 2. And now, can I simplify it more?
You can do 2, like the negative 4 turns into negative 2 plus or minus 4 root 3I.
Actually, you can divide top and bottom by 2. And you have to divide both terms by 2. So I have to divide both 4s by 2. And then the 2 in the denominator disappears.
Yeah.
So this is your final answer.
All right.
Well, not really. Excuse me. Find all roots.
So it'd be like x.
X minus that whole thing.
Yeah.
Which is 2 different roots. Now, the only thing here, let's talk about this for a second. Yeah, these are roots. They are not x-intercepts, by the way.
Mm-hmm.
When you have imaginary roots, they do not cross the x-axis. There are only 2 x-intercepts. One is at 0, and the other is at 4 for this function. And that is the main reason why you don't generally take those irreducible quadratics all the way down to their imaginary numbers.
Right.
But if they want the roots listed, they didn't ask for the factors. They want the roots. So another one is going to be minus 2 plus 2 root 3I, and then minus 2 minus 2 root 3I. So theirs are the 4 roots. And I assume that's what they mean by roots.
Yeah.
Because if they're asking for the zeros, I'm not sure you do go down to the imaginary. I guess you still do. It would be only if they ask for the x-intercepts that you wouldn't give them the imaginary ones. I guess.
Right.
If they ask for roots or zeros, then you do give it to them. All right, let's look at number 6. Okay. What are we going to do here?
You can separate x squared plus 9 into x minus 3, right?
No, that's not difference of perfect squares. That's actually the sum of perfect squares. And that doesn't separate. In other words, the first thing I'm going to do is set that equal to 0 and solve it. And then I'm going to set that equal to 0 and solve it. And I'm going to get 4 roots. Okay?
Right.
So when I set the first one equal to 0, what do I get? I get 3x squared equals 7. X squared equals 7/3. What's x equal?
X equals the square root of 7/3.
Well, plus or minus.
Plus or minus the square root of 7/3.
Always start whenever you're solving an equation by taking the square root of both sides, start your answer with the words plus or minus. Now, there is a little bit of a problem with that, and we'll get back to that in a moment. I'm not sure that they want your answer like that.
Right.
But let's solve the other one. The other one becomes x squared equals minus 9. So x equals what?
9 or 3i.
Plus or minus 3i.
plus or minus 3i.
In other words, you need to use that plus or minus whether it's a real number or an imaginary number. Like I said, whenever you solve an equation by taking the square root of both sides, even if one side is negative, then still begin your answer with the words plus or minus.
All right.
Okay, now let's go up and look at this answer. Notice the square root of 7/3 is the same as the square root of 7 over the square root of 3, which has an irrational denominator. So we really should rationalize this. How do you rationalize it?
Don't you square both sides? I don't.
First of all, we don't have an equation. We have a fraction. So I can't do anything I want to the top and the bottom. What I can do is multiply this by the number 1. That's it.
Okay.
Number 1 can take a lot of forms. I can multiply it by that. That's the number 1. And the advantage is it turns the bottom into a real number. And it leaves the top as that. So that, with the plus or minus, is really the way you should give the answer. If you were choosing from a multiple choice, you're going to see this on there, probably not that.
Yeah.
Just because most of the time, unless you're taking trig, if you're taking trig, that's the only time they really don't care if you don't rationalize the denominator. In fact, it's almost advantageous to not rationalize the denominator.
Right.
Not sure why that's such an important convention in math to begin with. In other words, that number is identical to that number. It just has a real denominator instead of an irrational denominator. Or it has, I should say, a rational denominator instead of an irrational. All right.
Yeah.
Number 7. Take the same strategy.
Yeah.
So what's the first thing I'm going to do?
So you put 5x minus 4 equal to 0.
Okay, solve that.
So you get x equals negative 4/5.
Positive 4/5.
Oh, okay.
In other words, when I move the 4 to the other side, it turns positive.
Right.
Okay. And then the second part?
Isn't that right? You have x, like x squared. Yeah. So x squared plus 5 equals 0. So you take the square root of 5.
Hold on. First move the 5 to the other side. What's it become?
Negative 5.
Okay. Now, what's x?
You take this. So x equals plus or minus the square root of negative 5.
Which is the square root of 5i.
Yeah.
In other words, you don't want to give the square root of negative 5 as an answer either.
Okay.
You always want to convert that to an imaginary number.
Okay.
Okay. Number 8, same thing. They don't have a big imagination. Yeah. The only difference on number 8 from number 7 and number 6 was we were able to solve those a little easier. In other words, we didn't have to use the quadratic formula. Even though they were imaginary solutions, we were able to get them by taking square root of both sides, which is relatively easy. This one, we're not going to be able to do that. That's a unfactorable quadratic. We're going to have to use the quadratic formula on that. So let's go through all of them. What's the first step here?
So x equals negative 1.
No.
Oh, with x equals 1.
Okay.
Yeah, I thought you wanted to go through the quadratic formula.
Okay. Well, oh, I see. Okay. Yeah, I get you. Yeah, you're right. Well, I do work. I do like to work from left to right. So I wanted to
Yeah.
take care of that one first. Okay. So using the quadratic formula, what's next?
So actually, it's -1 plus or minus 1 minus 4 um, times 1.
Simplify that.
So -1 plus or minus square root of -3 or square root of 3i.
Okay. We can write it like that as an intermediate step,
All right.
but then one more simplification.
Yeah.
What's that become? Square root of 3i? A lot
Yeah.
of people forget the square root. In other words, they tend to turn that into 3i. That's why I say whenever you have that, I like always the very first step is to make, lost my writing ability. What the heck? Oh, like an idiot now. I didn't have the writing ability turned on. Sorry, I got to go through this process again. And this is in a little bit. A little bit more. All right. So we got answers on that one. Are you satisfied with that one?
Yeah.
Number 8. Okay. For the following, synthetically divide. Find all real zeros of the dividend on the calculator. Graph the dividend by finding n behaviors, 0 and y-intercepts without a calculator. Write the dividend as a linear factor. Okay. Are you familiar? You know how to do synthetic division?
Yeah.
Okay. So let's do number 9. Tell me what I should write across the top.
So for the thing like outside of the box, it'd be -4/5.
Okay, that's what goes. Okay, yeah, I call that inside the box, but you're right. It's whatever the 0 becomes. In other words, I'm
Yeah.
going to set that equal to 0, and the 0
Yeah.
is -4/5, so that's what goes in the box.
Right.
Okay. And what goes across the top?
5, and then -21, -40, -6, and 4.
And you know that if there was a degree of r missing,
You just put a 0.
dummy variable, I would need a 0 for it.
Yeah.
Okay. In this case, there aren't any missing, so I don't need a 0.
Right.
Now, just go through it once for me, and then I'll know you know how to do it.
So you bring the 5 down and you multiply it by -4/5.
Okay, so that's -4 there.
Yeah. And then,
Whoops, hold on a second. No, it isn't.
oh, no, it's not. Yeah.
God, they're going to make us deal with all these fractions. Are you kidding me?
Yeah.
Why would they do that? What am I talking about? Yes, that is -4.
Right. Yeah.
Okay, and then you add.
Yeah, and then you add down.
Okay, now
Then you multiply that by -4/5.
so that's positive 20.
Yeah.
Then you add.
And then you add down. And then you
do it
multiply that by
again. That's
-4/5.
positive 16.
Yeah.
And you add. And you do it again, and that is -8. And you add. And that is your remainder.
Right.
Now there's something, I don't know if you've learned it yet, but have you learned the zero remainder theorem?
Kinda.
What it basically says is that if 5r plus 4 is a factor of that polynomial, then this has to be a zero remainder. So you can test whether something is a factor of something else by doing this synthetic division, and if you don't get zero, it's not a factor.
Right.
Okay. Now, so we synthetically divided it. We want to find all the real zeros of the dividend on the calculator.
Right.
Well, that means I'm going to put that into the calculator and find the real zeros. Now,
Right.
I can do that on Wolfram Alpha. Is that helpful if I do that? For one thing, if I do it on Wolfram Alpha, it gives you the zeros and you don't have to go looking for them. You have an Inspire, is that right, Hayden?
I have a TI-84.
You have a TI-84? That's harder. It's harder to find the zeros on the TI-84. Do you have this paper in front of you? If I close this out, will you be able to read it?
Yeah, I have it.
Okay. So you can read that polynomial to me? I don't mean to close it out, but I got to close it to open up Wolfram Alpha. And go ahead. What was the polynomial?
So it's 5r to the fourth minus 21x 21x cubed minus 40x squared minus 6x plus 4.
I could have probably used R. I think
Okay.
Wolfram Alpha would be able to interpret it. The nice thing about Wolfram Alpha is it shows you what you put in, and I can tell that we put it in exactly right. Okay. The other nice thing is it tells you all your zeros. All you got to do is scroll down. There's your 4 roots.
All right.
And, well, that answers the questions about whether roots need the imaginary ones.
Yeah.
What is this, a 4th degree?
Yeah.
Why do we have only one imaginary solution? Oh. I don't understand their answers here. Okay, so the real roots, there should be 2 roots and 2 imaginary roots.
Yeah.
I can't find the 2 imaginary roots. Maybe they expect you to. That's weird. The graphs, one is just zoomed way out.
Yeah.
They're the same graph, believe it or not. It's hard to tell. Look at the vertical scale on the bottom one, 500,000. So
Yeah.
500 isn't even going to show up as going below the x-axis.
Yeah.
But we can see it in a little more detail there. We certainly have a real root there. And we appear to have some kind of a 0 right here. I have never seen this problem before, where their real roots don't make sense. On a quartic,
Yeah.
you're going to have 4 real roots, or you're going to have 2 real and 2 imaginary. Imaginary roots come in pairs. This doesn't look like a pair. That's one answer there.
Yeah.
In scientific notation, no less. What the heck? 0.x? No, what that says is 0 times 10 to the minus fifth.
This is 0 with a bunch of zeros.
It is. What the heck kind of answer is that? Here I was going to show you the Wolfram alpha, how great it was, and it looks like it's...
So would that just be 5.6493? Because if it's 0 plus, like, 0 times whatever, it's just 0.
You just came up with the answer, I believe. In other words, there is no imaginary root.
Yeah, exactly.
There's 4 real roots.
They just wrote in a weird way.
That one, there's that one, that one, and that one. And yeah, they really put it in there in a weird way. And
because 0, because that's still I, like 4i is just 0.
What's that? Oh yeah, 5 is definitely in the ballpark, right? We can see that that real root is at 5 something, so that would be the answer. Okay.
So 0 times 10 to the negative 5th I is just 0. So it's just 0.
Yeah, it is. I've never seen that done ever. Plus, they list under real roots, and then they also list the same 4 roots under complex roots. What's with that? Huh. Oh well, maybe that wasn't the best one to illustrate. Let's see, what else did they want here? They had a bunch of questions on this thing.
Dividend and write the dividend as linear factors.
Okay, so we found the 4 real zeros.
Yeah.
Copy them off of Wolfram alpha if you want, or you can do it in your calculator and write down what you get. Graph dividend by finding n behaviors, zeros, and y-intercepts. All right, let's talk about n behavior. They do mean this as the dividend, right? Yeah, that's the dividend, that's the divisor, and the answer is the quotient and the remainder. Okay. First, for a moment there, I thought I was plugging in the wrong function. Okay, so we're looking at the n behavior of this dividend. There's only one term that matters. That's the biggest term. That's that, to determine n behavior. Okay? Let's talk about right-hand n behavior, because just realized from a previous session that the only n behavior you need to analyze is the right hand, and you can always figure out what the left is going to do based on the power, the degree of the polynomial. So to figure out the right hand n behavior, I basically plug infinity in for the variable. In parentheses, what does infinity to an even power turn out to be?
Positive infinity.
And positive infinity times a positive number is what?
Positive infinity.
So that's the answer for the right-hand end behavior.
Right.
And the fact that it is an even power tells us the left-hand end behavior is the same thing. If it was an odd power, the left-hand end behavior would be negative infinity.
Right.
Okay? So if I'm going to try to graph this just based on end behavior, well, I know I come from positive infinity and I go out to positive infinity.
Right.
So that's the beginnings of the graph. And the zeros, well, we had zeros there. We had three other zeros. One of them looked like it was maybe there, there, and there. If I remember right. And the y-intercept, how do we get the y-intercept?
It's just 4 because it's the end of the.
So we got to go through that point right there also.
Right.
So if I graph it in zoomed in scale, it's not going to look anything like Wolfram alpha. But each of these zeros had multiplicity of 1, correct?
Yeah.
In other words, we didn't have any zeros that had a multiplicity higher than 1. When a function has multiplicity of 1, it means it goes through the 0 on the x-axis. So this has to go through that to the other side. If it had multiplicity of 2, it would bounce off and go up. In fact, whenever it has even multiplicity, it touches the x-axis and goes the other way. When it has odd multiplicity, it goes through the x-axis. All of these have odd. So got to go back through that 0. Got to go through up through there. Got to go down through there. And it finishes like that. Now, I may not have the shape exactly right. For one thing, I didn't remember all 4 zeros. I remembered the one out here at close to 6. So it doesn't really matter where they're at. You get the idea, right?
Yeah.
In other words, no matter where I put those hash marks, I'm still drawing the graph something like this. I got to go through all the points. I got to go through the y-intercept. I got to go through all the zeros or bounce off of them depending on multiplicity.
Right.
Write the dividend as linear factors. Have they taught you how to do this?
Kind of.
Using the rational factor theorem?
Yeah.
Hold on a second. Dog's having a seizure. I just got to make sure she doesn't get near the top of the stairs.
Oh, yeah.
Keep my eye on her here. Well, the rational factor theorem is extremely complicated. And it takes a long time to use it, particularly on quartics.
Yeah.
A long time on cubics.
Yeah, I think she said she would go over it in class. I don't know.
Number 10 is a quintic. I have no idea how to do that one, other than the piece by piece.
Yeah, I think she said she would go over it in class. I don't think we have to do like D.
Let's take a simple one like 11. First of all, I'm not sure what they're trying to show here. Why did they start this problem off by dividing by that factor, which isn't even a factor? Unless I made a mistake on my synthetic division, which is possible, but if that were a factor, at least we'd have it down to a cubic, and then we'd be able to make progress with the rational factor theorem.
Right.
Kind of makes me feel like I made a mistake on my division, and that actually is a factor, and that they want us to deal with the dividend that results. I don't know, I'm a little confused by their instructions. So since that's the case, let's look at 11, and we'll solve 11 using the rational factor theorem. Okay? And we got 20 minutes, and it's liable to take 20 minutes.
Right.
Rational factor theorem says that if there is a rational zero, not an irrational, but a rational one, then its numerator has to be a factor of the constant, and its denominator has to be a factor of the leading coefficient, which in this case is 1. So here's all of our various possible rational zeros. We got, and they're always plus and minus. So you start with plus and minus 10, plus and minus 1, plus or minus 2, plus or minus 5.
Right.
Now my denominator, normally each one of these, I would have a denominator as also possibilities, but the only thing that's in my denominator is plus or minus 1. So that makes these 8 answers 8 possibilities for a 0.
Right.
Now, when you're dealing with a cubic, you generally do have one real 0. And that's because irrational factors come in pairs and complex zeros come in pairs. So it's hard to have 2 complex and 2 irrational. So there usually is at least one rational factor. Okay? And the way you get them is by checking each one of these using synthetic division until you get a 0 remainder. So, and that's kind of the beauty of synthetic division, is when it comes time to doing these kind of problems, it speeds it up a little bit.
Yeah.
Now, which one do you start with? In other words, it's a trial and error process. I do the ones that's the easiest math. So I start with plus 1 and then minus 1 and then plus 2 and minus 2 and so forth until I find a 0. Okay? So I'm going to put a 1 in there. Because all I got to do is go to this until I see that it is not 0 or that it's going to be 0. So I know you know how to do it. So I will do it. It's not going to be 0. So negative 1 doesn't work. Excuse me, 1 doesn't work. Let's try negative 1. I don't have to complete it and figure out what that number is. If it's not 0, then it's not my answer.
Right.
That's minus 18. That's not going to work either. Let's try 2. And believe it or not, this is the way to do it. As ridiculously complicated as this is, who knew? I mean, everybody thought that the quadratic formula was difficult, but there is no such thing as a cubic formula. In other words,
Right.
that's the only way to do these. Not going to work. Let's try -2. Not going to work. Try 5. There are some shortcuts here, but if you haven't learned them, there's no point in me mentioning them.
Yeah.
Shortcuts have to do with upper and lower bounds. Have they talked to you about that?
No, she hasn't gone over this.
I won't mention it then. 35, that's going to give you -18. That's not going to work. Let's try -5. I hate these problems, especially when you try all the numbers and none of them work.
Oh, yeah.
But that's rare, because like I said, it's hard for you not to have a rational factor.
Right.
Ah, this has promise. Bingo. -5 is our rational 0.
Yeah.
Not only that, that is the quadratic that's left. So if I want to write this dividend on number 11 as a series of linear factors, the first one would be what? X plus 5 or X minus 5?
X plus 5.
And the second one would be this quadratic, which does not factor.
Right.
So, depending on the rules they're using, in my book, this would be the answer. I've got, well, no, hold on a second. This might factor without being complex. Let's see, b squared minus 4. Yeah, it is going to. In other words, I do have to take that down further. It's just that I've got to use the quadratic formula. So up here in the upper left, I'll do it real quick since I know you know how. 3 plus or minus the square root of 9 minus a -2, so that's plus 8 is 4ac.
Yeah.
And divided by 2, so I've got 3 plus or minus the square root of 17 divided by 2. So those are my two irrational. Yeah, let's write it out. I got x plus 5, because that does turn into a linear factor. Give me the other two linear factors. Knowing the...
So that is 3 plus root 17 over 2, and then 3 minus root 17 over 2.
It's always x minus the 0.
Right.
So it's x minus the top number. So that would be x minus, and then I use double parentheses just so I don't make a mistake. So that's 3 plus root 17 over 2. And this one is x minus, still, not plus yet. Now that becomes minus.
Yeah.
So those are your three factors. And now if I remove the parentheses, which you do, then it looks much like if you'd have just put it without parentheses in the first place. You get x minus 3/2 minus root 17 over 2 times x minus 3/2 plus root 17 over 2. So those would be your three linear factors at the bottom there. And notice if we'd have just said x minus, we'd have gotten those two things. So
Yeah.
in actuality, you don't really need to use the inner parentheses.
Right.
Hold on 1 second. I took my eye off the dog. Sonny, you okay? In the middle of a seizure. Luckily, she didn't fall down the stairs. She was having one downstairs. She made it downstairs, but she's not out of it yet. Well, yeah, she's having a little tunnel, but she's a lot better. All right. Sorry about that.
Yeah, don't worry about it.
She at least wasn't a bag of bones at the bottom of the stairs, which I worry about, because when she goes into seizure, she completely locks up. I would hate to see what happened to her if she rolled down the, and she not only locks up, she kind of thrashes about. So it'd be easy if she was at the top of the stairs for her to go over.
Yeah.
But luckily she didn't.
Yeah.
Okay. So I guess that is a factor, huh?
Yep.
In this case, that is a factor. Now, we're going to run out of time. Well, we got 10 minutes. Do you have any questions as to which problems we should do with the rest of our time?
Not really. I mean, I pretty much just got it. It's just doing it.
Yeah, I think you know synthetic division.
Yeah, I understand how to do it. I just have to go through it.
I think you know how to find all the zeros on your calculator. Is that correct? On your TI-84, you know how to do it?
Yeah.
Certainly know how to graph that function and then use the trace feature where you have to put it to the left of the zero, to the right of the zero, all that garbage. Graph the dividend by finding end behaviors. What's the end behavior on 12? Start with the right-hand end behavior.
So it'll go down on the right?
What happens when you plug in infinity for x? What do you get? What's infinity?
Negative infinity?
No.
Or no, just infinity.
It's infinity. In other words, that's the advantage of doing the right-hand end behavior first, is that no matter what power you take infinity to, it stays at infinity. And I'm multiplying it by 2, so it's still infinity. So right-hand end behavior is goes up.
Yeah, and since it's cubed, left would go down.
Because it's an odd power, it's opposite. Yeah. So if I was going to try to graph that, first thing I'd do is I'd come up, I'd go up like that. And then I would use the zeros and the multiplicity. I know it's a cubic, so it's going to have at most 2 extrema, so it's going to look something like that.
Yeah.
It would look like this if it has 1 real zero only and 2 imaginaries. Might look like this if it had 3 real zeros.
Right.
Remember, the imaginary zeros do not cross the x-axis.
Yeah.
And I'm betting 3 is a factor of that.
Yeah.
You know, it makes me think we just did the math wrong on that.
Really?
Well, why would they give us one where it wasn't a factor?
Yeah.
Yeah, because if that is a factor, then it's going to reduce this to a cubic.
Right.
And in the cubic, we can kind of solve using that rational factor theorem,
Right.
where it's hard to start off using the rational factor theorem on a quartic, because that might find one of the zeros, which you then divide to get it down to a cubic, and then you have to do the whole process all over again.
Right.
So, yeah. Listen, do you mind if I go 5 minutes early tonight? My dog is back in seizure and she's...
Oh, yeah, don't worry about it. Don't worry about it. It's cool.
So, Hayden, I'll talk to you next time.
All right, cool. Thank you.
Bye-bye.
Bye.